All right, problem number 36 says, at any point of intersection of a solution curve given by the differential equation y prime equals x plus y and the line x plus y equals 0, and that part is key, the function y at that point is what? So here's the deal. If x plus y equals 0, then you know that y equals negative x. And you can plug that into this guy. If y equals negative x, then when you add x and y, you're going to get 0. So you know that y prime equals 0. So we don't know that the function equals 0. We can get rid of that. We don't know if we have a local max or a local min. We can pretty well be sure that we don't have a discontinuity. We're not told that anyway. We actually have no idea if we have one. And we know nothing about a point of inflection. But this is basically the first derivative test. We know that y prime equals 0. I'm sorry, we're going to have to use the second derivative test. We know that y prime equals 0, but we have no idea what the function is, and this is not a separable into differential equation, so we can't actually solve for the solution curve. So what we're going to have to do is actually take the second derivative using implicit differentiation and use the second derivative test. So the second derivative says this, that the derivative of x is just 1 and the derivative of y is dy dx. And if I sub in the original dy dx, which is x plus y, and then I sub in this relationship, I end up with the second derivative equal to 1, which is greater than 0, which means I have a concave up function where I had a tangent line with a slope of 0, which means that I have a local min at that point. Number 2 says, if I use, or actually number 38, number 2 on this page, says if you use Euler's method, 2 steps for delta x, with delta x equals 0.1, for y prime equals y with the initial value of 0, 1, then what is x equal 0.2, what y value does it give approximately? So I always set up a table for this. So I have my x and my y values, and my first values are 0 and 1. Then I find my dy dx, which if I plug in to my derivative equation, my y value goes in, so my dy dx is 1. So then I need a tangent line equation, which is going to be y equals the slope times x minus the x value plus the y value. So then I'm going to erase some of the work from above. Then when I plug my new x value, new x here, into the tangent line equation, I'm going to get out 1 times 0.1, so that's just going to be 0.1 plus 1. So 1.1 is my new y. So then I have to take this point here and bring it down to my next step. So 0.1, 1.1, the slope is 1.1, and then y value is 1.1. I'm sorry, the tangent line is y equals 1.1 times x minus 0.1 plus 1.1. My new x value is x equals 0.2. Plug 0.2 into here, I get out 0.1 times 1.1, which is 0.11, plus 1.1, and I end up with 1.21, which is b. For 39, I'm not even going to do this out. The error in using Euler's method is approximately what? What they're asking you to do is to go into your calculator and evaluate e raised to the 0.2, and then subtract from that our estimation from above of 1.21. And whatever that equals is going to be your answer to this. The reason why this problem is frankly silly is because they're never going to ask you this on the AP exam. If you could find the actual value of the function e to the 0.2, then you don't need to be using Euler's method. So the only thing that I want you to take from this is that your estimation ought to be lower than the actual value, since the e to the x function is concave up, so the tangent line will underestimate the actual answer.